A 125mm angle grinder may look simple from the outside, but its power begins with an armature assembled to extremely tight tolerances. The laminated steel rotor cores already contain hardened shafts and molded insulating end pieces. These plastic barriers prevent the copper windings from rubbing against the sharp steel laminations and causing an electrical short. The armature is locked inside a high-speed winding machine. Enameled copper wire is guided through the rotor slots and wrapped into carefully calculated coils. The thin enamel coating electrically separates thousands of wire turns, while allowing them to fit inside a compact space. Each section must receive nearly the same amount of copper. Uneven winding would create different magnetic forces and make the motor vibrate. The wire ends are then connected to individual commutator segments, allowing the current to switch direction as the rotor turns. The copper windings are coated with electrical insulating resin. The armatures rotate slowly while the liquid penetrates between the tightly packed wires. After curing under controlled heat, the resin locks every winding firmly in place. This prevents the wires from moving under centrifugal force and protects them from dust, moisture, and vibration. Without this treatment, repeated heating and rapid rotation could damage the enamel insulation and eventually cause the motor to fail. A precision cutting tool finishes the copper commutator, producing a perfectly round and smooth contact surface. This allows the carbon brushes to slide evenly without excessive sparking. A molded cooling fan is then pressed onto the shaft. When the motor rotates, this fan draws air through the grinder to remove heat from the windings. Finally, electrical and surge tests check coil resistance, insulation, and winding consistency. The waveform reveals defects that may be invisible during a normal visual inspection. The tested armature is combined with the stationary field coil to form the universal motor. Workers position the rotor carefully, so the shaft and bearings remain centered inside the housing. Electrical leads, brush holders, and switching components are prepared for installation. Automated equipment places these parts into the rear body while sensors confirm their orientation. Correct alignment is essential, because the rotor must spin with a very small, even air gap inside the stator without touching it. Every completed grinder is powered on for a no-load test. Workers listen for abnormal bearing noise, check vibration, and confirm that the spindle reaches speed smoothly. Electrical equipment measures current consumption. A motor drawing too much current may contain excessive friction, an incorrect winding, or a misaligned internal component. After passing inspection, the grinders are cleaned, arranged with their accessories, and packed into branded boxes for shipment. One kilogram of nearly pure gold is about to be transformed into a collection of Bitcoin-shaped investment rounds. Before any work begins, the metal is weighed with extreme precision to confirm that none of this valuable material is missing. The gold is heated with an intense torch until it passes its melting point of approximately 1064 degrees Celsius. As the solid pieces collapse, they merge into a bright, mirror-like pool of molten metal. Once fully liquid, the gold is poured into a rectangular ingot mold. The narrow shape makes the metal easier to roll later, while a steady pour helps prevent folds and large cavities from forming inside the casting. After solidifying, the hot ingot is removed and cooled in water. Its surface is rough and uneven because the outer layer froze first while the interior continued shrinking. The worker hammers the ingot to flatten high spots and begin breaking down the coarse cast structure. These repeated blows also reveal weak areas that could open into cracks during rolling. Although gold is naturally soft, controlling its shape at this stage is essential for producing a uniform sheet. The bar passes repeatedly between hardened steel rollers. The gap is reduced gradually, making the gold longer and thinner with every pass. Attempting to flatten the entire ingot at once would place excessive stress on the metal and could produce deep cracks. Small reductions distribute the pressure more evenly and provide better control over the final thickness. A digital caliper is used to check the strip because every gold round must contain a consistent amount of metal. The long sheet is straightened and positioned beneath a powerful blanking press. A circular cutting die punches out smooth discs one after another. The circles are arranged closely along the strip to minimize waste. The remaining gold framework is not discarded. It can be collected, remelted, and returned to the beginning of the process. Each freshly cut blank already has the approximate diameter of the finished Bitcoin round, but its surface is still completely plain. Steel dies containing the detailed Bitcoin design are installed in a hydraulic press. A gold blank is centered inside the lower die, covered by the matching upper tool and compressed under tremendous force. Because pure gold is highly malleable, it flows into extremely fine engraved lines without needing to be melted again. The pressure forms the large Bitcoin symbol, electronic circuit patterns and lettering across the surface. The blank is repositioned and pressed again to complete the opposite face. Accurate alignment is critical. Even a slight movement could leave the design uneven or create a distorted rim. Finally, every Bitcoin round is placed into a protective holder and paired with a certificate identifying its 9.9 gold purity. The sealed packaging protects the polished surface while helping buyers verify the product's origin and specifications. The Bitcoin symbol is decorative. The physical value comes from the carefully measured precious metal itself. What began as a 1 kilogram gold bar has now become a collection of precisely minted investment pieces. A high-quality badminton shuttlecock begins with hundreds of white flight feathers. Before they can be used, the feathers are washed and agitated inside a large rotating tank to remove dust, natural oils, and loose material. Cleaning also softens the feather shafts, making them easier to straighten and process. However, the feathers must be dried carefully because excessive heat can make the shafts brittle and more likely to split during play. The shaped feathers move through additional inspection stations. Cameras examine their outlines while mechanical guides position every shaft in exactly the same direction. Small differences that appear insignificant to the eye can change the shuttlecock's drag and flight path. The machine therefore separates the feathers into groups with closely matched dimensions and curvature. Workers perform another manual check, removing pieces with weak shafts, damaged edges, or uneven surfaces before they reach the assembly line. The shaped feathers move through additional inspection stations. Cameras examine their outlines, while mechanical guides position every shaft in exactly the same direction. Small differences that appear insignificant to the eye can change the shuttlecock's drag and flight path. The machine therefore separates the feathers into groups with closely matched dimensions and curvature. Workers perform another manual check, removing pieces with weak shafts, damaged edges, or uneven surfaces before they reach the assembly line. The partially assembled shuttlecock is placed inside a forming fixture. The machine adjusts the feather angles and spreads the skirt to a controlled diameter. Workers inspect the spacing by hand, correcting any feather that sits higher, lower, or farther outward than the others. The completed cone must be symmetrical because the feather skirt acts like an aerodynamic brake, keeping the cork head pointed toward the direction of travel. A trimming station then levels the feather tips and removes small differences around the outer rim. Completed shuttlecocks now enter balance and rotation tests. Inside a transparent chamber, airflow lifts or spins each piece while cameras observe its movement. A correctly balanced shuttlecock rotates around a stable central axis. If one feather produces more drag than the others, the body may shake, lean, or drift sideways. Additional machines shape and finish the cork area, while workers inspect the skirt, binding, and overall alignment before the final grading stage. The shuttlecocks receive their finishing bands and are sorted according to flight performance. Different speeds may be selected for different temperatures and playing environments because air density affects how quickly a feather shuttlecock travels. Some samples are struck across a test area to confirm their distance, stability, and recovery after impact. Only the pieces that fly consistently are packed into protected tubes. What appears to be 16 simple feathers is actually a precisely balanced aerodynamic structure, where every curve, hole, and thread affects the final flight. A decorative glass jar may begin with very inexpensive raw material, yet the finished product can sell for many times more. The process starts with large quantities of broken clear glass, known as cullet. The pieces are fed through crushing equipment until they become small, evenly sized fragments. Reusing cullet reduces waste and lowers the energy required for melting because recycled glass softens faster than completely new raw materials. The crushed glass is combined with a carefully measured mineral mixture. Most clear household glass is based on silica sand, with additional materials that lower the melting temperature and improve chemical stability. Workers load the ingredients into a rotating mixer where the fine powders and glass fragments are blended evenly. Poor mixing could create streaks, bubbles, or weak areas because different sections of the batch would melt at different rates. The prepared batch is weighed before being transferred into the furnace. Consistent weight helps operators maintain the correct glass level and composition during continuous production. Inside the furnace, temperatures high enough to soften the mineral mixture transform the rough batch into a glowing liquid. The molten glass must remain hot long enough for unmelted particles and many trapped gases to disappear, producing a cleaner and more transparent material. A glass worker inserts a long blowpipe into the furnace and gathers a controlled amount of molten glass onto its end. The glowing mass is continuously rotated so gravity cannot pull it to one side. The worker rolls it across a smooth steel surface, known as a marver, to center and slightly cool the outside. A small bubble is then blown into the middle, creating the hollow core of the future jar. The enlarged bubble is lowered into a forming mold. As air enters through the blowpipe, the soft glass expands against the inner walls and adopts the required diameter, base, and neck profile. The mold provides repeatability, but the workers must still control rotation, air pressure, and temperature. Too much pressure can create thin walls, while glass that is cooled too far may not reach every part of the mold. The newly formed vessel moves through several finishing stations. Flames reheat selected areas while rotating tools refine the opening, foot, and decorative rings. Continuous rotation keeps these features centered around the jar. Fire polishing also melts away tiny cutting marks and sharp edges, leaving a smoother, clearer finish. This stage requires careful heat control because one overheated section could sag and distort the entire body. After cooling, workers inspect the glass, wrap each vessel in protective paper, and place it inside a reinforced box. The jar is then fitted with its lid and decorative collar before being filled with water for a final visual check. The raw glass itself may be inexpensive, but skilled labor, furnace energy, tooling, rejected pieces, finishing, packaging, and transportation all contribute to the much higher retail price. This wood-like flute begins with nothing more than soft clay. The instrument is actually a ceramic ocarina, a type of vessel flute whose sound is produced inside a sealed hollow chamber. Fresh clay and reusable offcuts are compressed into dense cylinders. This preparation removes trapped air and creates an even texture. Air bubbles are dangerous because they can expand during firing, causing cracks or destroying the instrument completely. The clay cylinders are then flattened and rolled into sheets of consistent thickness. Uniform walls are essential. Clay that is too thin may collapse in the mold, while excessively thick walls dry unevenly and can affect the internal volume of the sound chamber. Each clay sheet is positioned over a shaped mold and covered with a thin protective film to prevent sticking. A powerful press forces the material into the cavity, forming the curved front and back sections of the ocarina. Using matched molds allows every instrument to maintain almost the same external shape and internal capacity. This consistency is especially important because the size of the enclosed air chamber directly influences the instrument's basic pitch. The most sensitive work takes place inside the mouthpiece. The craftsman carefully carves the narrow air channel and shapes the sharp edge that divides the incoming stream of air. When the player blows into the instrument, air travels through this channel and strikes the edge, creating vibrations inside the hollow chamber. If the passage is too wide, too narrow, or slightly misaligned, the ocarina may sound weak, unstable, or fail to produce a clear note. Every internal surface is therefore refined by hand before the body is sealed. Liquid clay, known as slip, is brushed along the joining edges. It acts like a ceramic adhesive, helping the two molded shells bond together. The halves are carefully aligned and pressed into one complete body. Workers compress and smooth the seam with small tools, gradually making the joint disappear. The chamber must be completely airtight because even a tiny leak would reduce air pressure and weaken the sound. The mouthpiece, outer curves and finger holes are checked again, while the clay is still soft enough to correct. The assembled instruments are refined with a brace of blocks, damp sponges, and metal tools. Rough marks are removed, the holes are cleaned, and the mouthpiece is kept completely open. A brush is then dragged across the surface to create a realistic wood grain texture. Although the finished instrument looks as if it has been carved from timber, its body remains entirely ceramic. The ocarinas must dry slowly and evenly before firing. If moisture leaves one area faster than another, the body can warp, the seam can reopen, or small cracks can form around the holes. Workers clean the holes, refine the mouthpiece, and smooth the surface. A brush creates a detailed wood grain pattern, making the ceramic instrument resemble carved timber. It is then dried slowly to prevent warping and cracks. Finally, each instrument is played and inspected by hand. The test reveals whether the airflow is clean, the notes respond correctly, and the tuning remains balanced. What appears to be a simple object made from mud is actually a carefully engineered acoustic chamber, where every curve, opening, and millimeter of clay contributes to the final sound. From soft clay and recycled glass to pure gold, precision power tools, and perfectly balanced shuttlecocks, every product in this video reveals the same hidden truth. Remarkable results come from controlling countless small details. Skilled hands, specialized machines, and carefully selected materials work together to transform ordinary beginnings into valuable, reliable products. Which manufacturing process impressed you the most? Share your answer in the comments, and don't forget to like, subscribe, and turn on notifications for more incredible factory processes from KenTT Machine.